implicit differentiation. In this session, we will try to get the derivative of the equation, which is presented in the implicit form. Let's look at these old equations that we just met so far, we were dealing so far. We can see both of them, because the third one is just the general form. The first one, the product, the compound function. The second one is simply defined explicitly as a y in terms of x, in terms of independent variable x. X times sine of x, we will use the product rule for the first one, square root of x squared plus 1. In order to differentiate, we will use the chain rule. And in general, this is the equation. Y is basically isolated on one side, and the entire x independent variable is on the other side. That's we have no problem to find these derivatives. But now, what happens if we will have an equation? I have to maybe be careful saying functions, because the first one and the second one, when we will draw these curves in the xy plane, they are not exactly a function. They will fail a vertical line test. The first one, we all recognize, it's the equation of the circle. Yes, with the center 0, 0 and radius 5. The second one is a beautiful loop we call volume Descartes. I can show you in a second. And is also not a function. But when we will explicitly solve this equation for y, and possibly this one, yes, then we will get each part will be a function. Of course, the first one is the second y squared, the second degree. That means we will expect two equations. This one is y cubed. That means I am assuming we will expect three different parts. Okay, but this is not a point of this implicit differentiation concept. Yes, but I'm just saying, just in case, if we would like to use the old explicit form. That's what we will do. Before I introduce the implicit differentiation, a little bit faster and efficient way to get the derivative, because even if these are not a functions, they are still a continuous differentiable curves. They have derivative at every single point. I mean, we have to be careful, almost every single point, unless we have a vertical tangents, almost at every single point and on the curve, on the domain. That's before I show you the implicit differentiation, let's actually take this circle and actually let's force it and let's solve it, because this one is extremely easy. Let's solve this equation for y. The first step is to subtract x squared from both sides and then take the square root of both sides, of course, plus and minus. And we may guess positive square root, negative square root, upper semicircle and the lower semicircle. Now, what we will do, we will get the derivative. We can see now it's easy, just the outer function times the derivative of the inner function. The derivative of the outer is the derivative of the square root times derivative of the inner function, negative 2x. And you may maybe pause the video and get the derivative, but you're supposed to get this. Oh, I think I didn't simplify correctly. It means the final answer will be negative x over square root of this quantity. Okay, and the same, almost the same on this side, which I also didn't. I think I wanted to cancel out x over 25, square root of 25 minus x squared. Okay, that means that's the derivatives. And when we have this, we of course have the domain only between negative 5 and 5. Because we have the square root, automatically we can say domain for this function is interval between negative 5 and 5. Okay, but that's it. That's the known way. What I would like to do? Let's actually, okay, that means this was the first equation. When we look at the second equation, which, as I promised, this is a beautiful loop. That's the equation. Yeah, we may think we just drawing like this. Okay, it's a beautiful loop. Maybe I can remove my drawing. And it's called volume Descartes. Definitely not a function, definitely continuous and differentiable, almost at every single point of the domain, except the vertical tangents, which derivative is undefined, but we can still prove this. Okay, but now, if I would like to also force it and solve for y, it will be a little bit complicated. Yeah? We will not spend time, because we will need lots of time, unless we ask a computer, whoever the computer is. And I did ask the computer, and let's see. You will probably not even believe it, but that's the equations. And as I mentioned, we will have the first one, which represents that part. And then this is the second and the third one, because we have addition and subtraction. Addition and subtraction. Okay, that's and all of them, all of the three parts, this one, and this one are the function. But we don't even want to look at this. Yes, we don't even want to look at this, because, and thinking about lots of chain rules, we may do it, we may get the derivative, but we don't want to do this way. That's, we definitely need a shorter way. And the shorter way is called implicit differentiation. Let's see. Implicit differentiation method. Okay, that's me. First of all, let's see what we will do. The first step is we will take the implicit equation like it is. We will not solve for y, we will not solve for x, we will not rewrite. We will just take it like it is, like the first one and the second one that we just saw it. We will take it like it is. But we still have to defined, we have to state that x is independent variable, that's fine, but y, which we don't want to solve for, it's a function which depends on x. That means y equals to the expression of x, f of x. We don't want. We may also think that y is defined implicitly because it's hidden, not directly. But we may also think that y, behind y, is a function. We don't know this function, but it is a function. We can call inner function, because the implicit differentiation is kind of like a chain rule. Okay, that's me. Now what we will do, we will take the derivative with respect to x of both sides, of both original sides. And I have a couple of examples to just show you. When we will differentiate derivative with respect to x, cosine of x, it will be just sine of x, no problem. Derivative with respect to x of x to the power of 4, 4x cubed, no problem. But now we will also see the implicit form of the y function, derivative with respect to x of cosine of y. That means we will differentiate cosine. Derivative of cosine is negative sine of y, cosine of y, sine of y, and follow the chain rule times derivative of the inner function, which is derivative of y with respect to x. Or we can just say y prime, negative sine of y times y prime, if you prefer this. But y prime doesn't have lots of details of independent variable. Yeah? That's, we can see we have to follow that. It's a chain rule basically, but we have to say cosine of y is negative sine of y times derivative of y, dy dx. Okay, now the same for this one. Derivative with respect to x of y to the power of 4. Derivative of y to the power of 4 is 4y cubed times derivative of y, dy dx, because y depends on x. We don't know that formula, but we have to state this. That means 4y cubed times y prime, if you like this notation. Okay, that means just remember this and then apply. Let's see. We will actually do this again, but we will use the implicit differentiation. Okay, x squared plus y squared equals to 25. Implicit differentiation means that I will differentiate with respect to x both sides, left and the right. And let's see. Derivative of x squared, just 2x. Derivative of y squared, it is 2y dy dx. Derivative of 25 of the constant is 0. That we can see 2x, 2y dy dx. We don't need this for the independent variable because it's derivative of x with respect to x is just 1. And derivative of constant is 0. Okay, and now because we're looking for we're looking for the derivative dy dx. Let's solve this equation for dy dx. We will subtract 2x and we will divide by 2y. That means this is the derivative of that circle. And now you may think we just did this derivatives in the explicit form. And you probably remember slightly different formula. That's mean now let's compare just to see how this works. Okay. Oh, no typo now. Upper circle, I mean semicircle, lower semicircle, that was the derivatives. Now we did implicit, which implicit differentiation always results in the most general derivative form. That means I hope you can see the connection. That means derivative of the entire circle in the implicit way is negative x over y. The first thing that you may notice, the answer, the derivative depends on x, as always, but also depends on y, which sometimes for some applications we will need additional steps. But if you compare these two, you can see this was y. That means if I replace the square root of 25 minus x squared with y, then yes, I have the same equation. Now we can say this is, what we can say? The square root, maybe I can write, because I have the square root, you can probably see, it's just negative. It will be negative y. That means this is negative y. When we will subtract, it's exactly the same. That means, yes, we do have it connection. This is the same. But that form is the most general form. If we will solve the equation for y, I mean, if we will solve the expression for y explicitly, we can substitute and we will get these formulas, this one and this one. Okay, that means the implicit differentiation works. Okay, let's practice because now we have to take this equation. This is the beautiful loop, volume Descartes. Now, find y prime if the equation is defined x cubed plus y cubed equals to 6xy. Then find the tangent to the volume of Descartes at the point 3, 3. Let's see. And also, at what points in the first quadrant is the tangent line horizontal? We have to find the point, x and y coordinate. Okay, that means I think I type it. Let's see. We have to be really careful, okay? That's part A. We're taking the equation and we will differentiate like it is with respect to x, both sides. Okay, no rewriting. So now we have to be careful. Derivative of x cubed, it will be, you may say aloud, as always, do you know, even if you're watching this later, even if you're rewatching, you can say aloud. Derivative of x cubed is 3x squared plus derivative of y cubed, it is 3y squared times dy dx. Because this is function hidden behind y. We didn't solve it, yes? We know that y depends on x. And we're looking for the derivative, which is dy dx, or y prime, f prime. Okay, now the right-hand side, derivative of 6xy. We definitely have a product. Please do not miss this. I can maybe draw a dot. Derivative of 6x is 6 times y plus 6x times derivative of y is dy dx. Let's see. 3x squared, 3y squared dy dx. Derivative of 6x is 6 times y plus 6x times derivative of y, which is dy dx. Perfect. Really important. Yeah? Always remember, derivative of x, 1. Derivative of y, dy dx. And now let's solve it for dy dx. Now it's just algebra. I will subtract that part because we can see this part, this expression, and this one, they includes dy dx. We have to isolate them on the left-hand side, and then I subtracted 3x squared. Now I factor out dy dx, and I will divide both sides by this expression. We may also see 3 is a common factor. We may factor out 3, 2y minus x squared, and then y squared minus 2x. Perfect. This is the derivative. And if we will have the equation for y, we will substitute, but we may keep this form, the most general form of the derivative. Part A. Part B is asking for a tangent line. Yes, tangent line at the point 3, 3. I type it, but let me just say, I will start with the point slope form, point slope form. And this is 3, and that's slope. And this is 3. And slope, of course, is this. We can just substitute instead of x3. And also you may notice we will need y value. We usually don't need the y value. Okay, we will substitute 3. That means substitute because it's 3, 3. Substituting 3, we will get -1. And again, point slope form, that's the slope. And distributing -1, +3, another +6. That means this line has an equation of -x plus 6. And I think makes sense, slope negative, y-intercept 6. Okay, part B is done. Now part C. We have to find the x value where, actually let's come back, somewhere for the part C, in the first quadrant. That means I would say it's somewhere here, where the tangent is horizontal. We need this x and this y. I don't know, we may definitely say, if we trusting my scale, but I think it's less than 3. Yes, the point will be less than 3, but let's, yeah, this is a horizontal tangent. And we know that horizontal tangent has the slope 0. That means this is slope, derivative is 0. Okay, let's get the formula. That was the formula. This fraction must be 0. Fraction is 0 if and only if numerator is 0. Yes, because denominator is never 0. If the denominator is 0, yes, we can get some other, like we know that derivative is undefined in this situation, but we're not looking at this. We just want this numerator 0. We want, that means when this is 2y minus x squared is 0, then the whole derivative is 0. Then the slope of the tangent at this point is 0. But we may see we have a small extra step to think of, because I cannot really solve, because this doesn't depend on x, only if we will have a normal explicit. We've got the relation between x and y. That we will know that y, I just solve it for y because it's linear, y equals to 1/2 of x squared. But what is x? To compute y, we don't know. That's what we will do. We will need, since we have two unknowns, x and y, we will need another equation. And theoretically, we will have a system of two equations, then it's not a problem. We can solve it. That means this is one relation. Yes, I can even, maybe green, because I was using green. This is one relation. But let's come back for a second. We can see this is that point. But this point, that means this was the relation based on the slope. We can also see that this green point that we're looking for also belongs to the curve, because always tangent line has one point, like the common point of intersection, I can say, which intersect, yes, the point when the tangent is tangent, when the tangent is attached, point of the tangency, with the blue curve. That means we may basically take this blue equation, the original equation, as a second equation for the system of the equations, okay? That means when I take the original equation, what was the original equation? Let me maybe draw here, was x cubed plus y cubed equals to 6xy. That means this will be the second equation, which includes x and y. This is the first one. Now, when I substitute y, because they both satisfy the same point, I can get the equation just in terms of x, and I can solve it for x. And I did this. Oh, this is supposed to be also y, x squared over 2. Okay. Oh, yes, I did here. That means now we can see I replace y with the relation for the horizontal, for the slope being 0. Okay, that's please remember, always use with this implicit situation, use the original equation. I mean, whatever equation we have in the question that relates x and y together. Okay, let's see. This one will be x squared cube, which is x to the power of 6. 2 cube is 8. I have this one, and I think I multiply everything by 8. Yes, each, like I can multiply this by 8, this by 8, and this by 8. Let's see what we will get. 8x cubed, that 8 is cancelled out, which is just x to the power of 6. And this one can be cancelled out. 4 times 6 is 24. X times x squared is x cubed. Okay, now we have the like terms. Okay. I can subtract 24x cubed. It will be negative 16x cubed. X to the power of 6. We can factor out x cubed, the common factor. And now x cubed is 0, or x cubed is equal to 16. This one is theoretically, because we're looking just in the first quadrant. This is the origin. That's we're looking for that point. Cube root of 16. Okay, cube root of 16 is definitely more than 2, because cube root of 8 is 2. And cube root of 27 is 3. That means, I don't know, 2.2. But we don't have to approximate. You can leave it cube root of 16. And if I take this cube root of 16 and substitute here to the y expression, we will get cube root of 16 squared over 2. This is the y value. That means that's the green points. Actually, I supposed to use the green. That's the points where coordinates of the point when the tangent is horizontal. Let's see. Oh, 2.5. My approximation is not that good. I thought that we are far away from 27. It's fine. As I said, we don't have to. Yeah, you may. And yes, makes sense. Yes, 0, we will not use 0, but tangent horizontal is at this point. I can say cube root of 16, and this one will be cube root of 16 squared over 2. This is the y value. and this is the x value. Okay? Beautiful. Yes, we know the concept. Okay, that's everything. And I have one more question, just to finalize this introduction to implicit differentiation. And you can check the other questions and you can practice. Okay, now let's look at this one. Lots of derivatives. That's what we have. A parcel of air rising quickly in the atmosphere will decrease in temperature and increase in volume. Okay, yes, decrease the temperature and increase in volume. Yeah, we can imagine increasing the volume of the balloon, for instance, if it does not exchange heat with a surrounding air. Yeah. For sufficiently dry air, the relation between the temperature and the volume is given by this equation. Okay, temperature times volume to the power of 0.4 equals to a certain constant C. Temperature is in kelvins, volume is in the cubic meters, and time that passes, it's in hours. Okay, and now we have to calculate part A, derivative, the rate of change of the temperature with respect to volume, and explain what it represents. Be sure to include units. Okay, let me copy, or maybe I can do here, part A. We looking, first of all, we have the equation. Temperature, volume, to the power of 0.4 equals to constant. And we're looking for this. We will differentiate temperature with respect to volume. That means volume is actually the independent variable. Derivative of V will be just 1. Let me just do. We will differentiate temperature with respect to volume. Always look what is dependent, T on the top, independent in the denominator, V. Okay, let's use the implicit differentiation because we will not change the equation, we will take like it is. That means now definitely product. Derivative of T with respect to V will be just dt dV times the second function plus T, and now derivative of V. V is independent. That means it will be like x to the power of 0.4. Derivative is 0.4, x to the power of 0.4 minus 1, 0.6. 0.4, V to the negative 0.6. And then derivative of the constant, 0. Let me I just want to align. Derivative with respect to V. Okay, that's it. Then we can just solve it for dt dV. Let's solve it. dt dV, derivative of the temperature with respect to the change of the volume. We will subtract T, 0.4 V negative 0.6 power, divide by V to the power of 0.4. We can definitely combine negative T. Actually, let's use the constant in front. Negative 0.4 T divided by V, because when we drop down, this is to the negative, then putting in the denominator, we can have 0.4 and 0.6 multiplying the same base, we can add those. That means it will be basically V to the power of 1. Yes, I hope we can do this. Okay, that means this is the derivative negative, it's negative. Okay, it's actually, yes, because it says that the increase in volume, but when the temperature decrease. That means, yes, the temperature, the rate of change of the temperature, it's with respect to the volume, it's decreasing. And now let's actually say the unit. Unit will always, how can we find the unit? This Leibniz notation, dt dV, it's telling us units. the units of the temperature, which is kelvins, right? That means that's kelvins with respect to the volume, meters cubed meters, okay? And what this means? This basically, this expression measure quantitatively the change in the temperature of the air parcel as the volume changes with respect to the volume, okay? I think makes sense. Okay, now let's do dV dt the other way. How the volume is changing with respect to the temperature. Yeah, that means the part B will measure quantitatively the change in the volume of the air parcel as the temperature change. Okay, let's see. That's we have to find dV dt. Temperature, volume to the power of 4 equals to the constant. Now I will differentiate volume with respect to the temperature. Differentiate volume and temperature is independent variable. Okay, again, product. That's in what we will have. Temperature is independent. Derivative of T is 1 times, yes, derivative of T is 1 times V to the power of 0.4 plus T. Now, derivative of V is depends on temperature. That means derivative of V to the power of 0.4, it will be 0.4V to the negative 0.6 times dV dt. And derivative of the constant 0. Okay, and the same thing, we can just solve it for dV dt. We will subtract V to the power of 4 and divide by T, 0.4 V to the negative 0.6. And when we move that V on the top, 0.4 and 0.6, because this will become positive, will give us 1. That means we will have negative V over T times 0.4. Oh, I supposed to say 0.4. Okay, and now V volume is meters cubed, temperature is kelvins. That's the units. And as I mentioned before, this measure quantitatively the change in the volume, yes, of the air parcel as the temperature change with respect to the temperature. Okay, beautiful. Now let's look at C. Find dt with respect to the time. That's we have to find how the temperature is changing as the time passes, assuming that both time and volume are the function of, I mean temperature. Temperature and volume are the function of T, of time. That's me, and this will basically, we can see dt, the rate of change of the temperature with respect to time. That means this will measure the quantitatively the change in the temperature as the time passes. Okay, with respect to time. That means let's see the rate of change of the temperature with respect to time. We will differentiate temperature with respect to time. We will function temperature, but both of them, T and V, depends on time. And we have T, V to the power of 4 equals to derivative of the constant. We can see implicit differentiation. Okay, it's me now product. Derivative of T is dt with respect to time times function plus T. Now, derivative of V to the power of 0.4, it will be 0.4 V to the negative 0.6 times dV dt, because V also changes with respect to time. Constant remains constant, derivative of constant 0. And now we just have to find out, solve this equation for derivative of the temperature with respect to time, and we know what to do. We can move T, 0.4, V negative 0.6 dV dt divide by V to the 0.4. And again, we may drop this down. 0.4 and 0.6 together will be 1. It means the final answer, let me put this, dV dt, it will be, I can put dV dt, it will be negative 0.4 t divided by V. Yeah? And we may notice this answer is actually part A. Do we see this? Which is dt dV, derivative of temperature with respect to the volume, and that, yes, that's part A, and times volume with respect to time. That's we could do this right away. Derivative of the temperature, and I mean, yes, temperature with respect to time equals to derivative of the temperature with respect to volume times derivative of the volume with respect to time. Beautiful chain rule. But we may also do this way. Yeah? But if you realize it's actually part A, actually everything is the answer. Yeah? Negative 0.4 t over V dV times dV dt. I don't like dividing this. Okay, we almost there. Just the units, but it's just temperature, which is Kelvin, and what was minute? Oh no, was hours. Kelvin with respect to hours, how the kelvins change with respect to time. Really nice. Okay, really nice. And then what is part D? Part D is asking to compute what we've got in part C, having just the information. Compute the rate of change of the temperature with respect to time at the moment, because that's calculus. We need that moment when the volume is 10 cubic meters, temperature is 295 kelvins, and volume is increasing at the rate 1 cubic centimeters per hour. That means the rate of change of the volume with respect to time is basically 1 cubic meters per hour. Okay, that means 10 and 2, let me copy this. The rate of change of the temperature with respect to time. What was the answer? Negative 0.4 t over V, and the rate of change of the volume. Okay, negative point. T is, what is temperature? I think was 295 divided by, oh, my pen is funny, by 10 and 1. I will skip the units because all of the units match. And when we multiply everything, we will get negative 11.8. And the units are temperature over time, kelvins over hours. Okay, like around negative 12 kelvins per hour. I mean, around 12, 11.8 kelvins per hour decreasing. Yes, the temperature will decrease. Okay. And the last one, I mean, we have two more. Find dV dt. Find dV dt. Okay, we have, assuming that both are functions of time. Okay, that's now we have to do, basically, we can take this equation, correct? We can say, what we can do? Like the same like in the part C, but we will solve for dV dt. Yeah, that's part D. You will start with this. Shall we do it? I mean part E. Okay, we have to find, we will dV dt. And this was temperature, volume, dV, the rate of change of the volume with respect to time, and the constant, because this was the equation, yes? We know I'm just taking this equation and in the form of the implicit differentiation. Let me double check. Yes, dV dt. and both of them are function. I could take this equation right away, okay, but let's do it from the scratch. Then you will practice. Derivative of temperature will be dt v 0.4 plus temperature derivative of the volume, like the v to the power of 4 will be 0.4 v to the negative 0.6 times dv dt and the constant. And now solving for dv dt, we will have negative v to the power of 4 dt with respect to time, divide by time 0.4, just flipping v to the negative 0.6. And when I take this v to the negative 0.6 to the top, it will become positive 0.6. It will be just v and 0.4 t dt dt. Okay, that's this part E, and part F with all units will be, because we did calculate the volume with respect to time, volume over the time, cubic meters over the hours. And part F is asking the same thing, but the temperature, the rate of change of the temperature is 2 kelvins per hour. That means the rate of change of temperature with respect to time is 2 kelvins per hour. That means let's just subtract part F and we will be done. And this is a nice question. You probably recognize the rate of change of the volume with respect to time equals to negative volume, which is 10.4. Temperature was 295, and the rate of change of the temperature was 2 kelvins. And when you use the calculator, it will be negative 10 over 59 volume meters cube per hours. Or we can even, actually this is direct number. This one will be 0.169 cubic meters per hour. Actually negative. Okay. That's we have everything. We use the implicit differentiation in quite, yes, nice way. Okay, I have more example. That means you may check the next video, but enjoy this introduction to implicit differentiation. Thank you.